Solving ordinary differential equations. A simple first-order differential equation has the general form dy dt equals to f of t comma y, where dy dt is the change in y with respect to time, and f of t comma y is any function of time t and the value y. This is a differential equation because the derivative y is dependent on y itself. So here's an extremely simple differential equation. Dy dt is equals to negative y. We can solve this ODE by separation of variables and then integrate. So what we can do is try to isolate y on one side and try to isolate t on the other side. So if we multiply both sides by 1 over y and dt, we will have dy y is equal to negative dt. Now we can integrate both sides to obtain ln of y is equals to negative t plus c, where c is a constant. Now we can solve for y by taking the e of both sides. And we'll have c is equals to e to the parentheses negative t plus c. We can rewrite the above equation in the form of y is equal to c times e to the negative t. Now c is a constant here, so we need an initial condition to solve for c. So let's say that at y equal to 0, our value, at x equal to 0, our y value is 1. So we can plug this equation plus 0 back into our equation, and we'll have and solve for c, and we'll find that c is actually equal to 1. And once we have c, we'll plug it back into our equation. We'll have y is equals to e to the parentheses negative t as our final solution. So y is equal to e to negative t is our answer to the differential equation dy dt is equal to negative y. Now, we can solve the ODE in MATLAB quite easily using the solvers, ODE solvers in MATLAB. So MATLAB provides a large set of ODE solvers for us to use, each with its own degrees of accuracy. The ODE solvers we're going to use is ODE 45. So ODE 45 looks something like ODE 45 function t-span y0, where function is the function handle for the function that gives us the dy dt. T-span is the range of t values, and y0 is the initial condition. We will return two outputs, t for the t values, y for the y values. So let's try to solve for dy dt equals to negative y in MATLAB. So first thing we need to do is actually create our ODE function. So let's call this simple ODE. Here I will create a function that will give me dy dt. So function, my output will be dy dt is equals to simple ODE t comma y. And my dy dt is equals to negative y. This is all I need. So the first thing I do is actually create my ordinary differential equation, ODE, here. dy dt equals negative y, and put it into a separate function. Next step, we can simply call it the ODE solver, ODE 45. So let's say t comma y is equals to ODE 45 parentheses. So assign simple ODE. So this is basically the function handle for my simple ODE. I want my t-span, which is basically my t range, to go from 0 to 5. I want my y value, I want my y0, which is my initial condition, to be 1. Now I have the t values and y values. So finally, let's plot our y versus t graph. Plot t comma y. When we look at our equation here, look at our graph here, the graph should make sense, as the solution to the ODE is y is equal to e to negative t, which is an exponentially decaying function. Now consider the following problem. An object is dropped from a height of 500 meters. Find the equation to give us the position of the object as a function of time. Recall that in physics, we can model a falling object using the equation y is equal to a times t, where v is velocity, a is acceleration due to gravity, and t equal to time. We'll assume that the acceleration due to gravity is negative 9.81 meters per second squared. If we let y of t be the height of an object at time t, we can see that the velocity is equal to dy dt. So if we substitute v equal to dy dt and a equals to negative 9.81 into the equation v equal to at, we'll get the following differential equation. Dy dt equals to negative 9.81 times t. If we were to solve this ODE using a method similar to what we did above, we get the equation y is equal to negative 4.90 t squared plus c. And given our initial condition, where at t equal to 0, we're at 500 meters, we can solve for c, which gives us c equal to 500. So the equation that gives us the position of the object as a function of time is y is equal to negative 4.90 t squared plus 500. Now let's try to solve this in MATLAB. So dy dt equals to negative 9.81 times t. So first thing I want to do is create my actual function. So edit velocity function. Function dy dt is equals to velocity function of t comma y. My dy dt is simply equal to negative 9.81 times t. So this will be my function. Now all I have to do is again simply call my ODE 45 function. So t comma y is equal to ODE 45 assign velocity function. Assign velocity function. My t span, I want to go from 0 to 10. I want my initial value to be 500. Now, let's plot our t versus y graph. Or plot t comma y. And we see our equation here. We see our graph here. Now this graph should make sense. Initially, we start off at 500. When we drop the object, it goes through an exponential decrease, and the point is eventually at around 10 seconds, it will fall to the bottom. Now, we can use polyfit to find the equation of a polynomial, the best fitted curve. So if we do y is equals to polyfit t comma y comma 2, where 2 is the degree of the equation that I would like to approximate. Polyfit. P-O-L-Y. Polyfit. It gives us the following three things. Y is equals to negative 4.9, negative 0, and 500. So this actually corresponds to the equation y is equals to negative 4.9 t squared plus 500, which makes sense.